we continue what we were discussing. In the case where the energy separation between 2s and 2p is large, the molecular orbitals formed have this order as far as their energies are concerned, but if the separation between 2s and 2px is 2s and 2p is not that large, then what happens is that the order of the orbitals change, and what happens is that this sigma g 2p actually goes above the pi orbitals, and that is what is shown in this picture. But then of course, you should realize that this sigma g 2p as it is written, it has contributions from 2s as well as 2p, and therefore, strictly speaking it is not completely correct to call it sigma g 2p, but we will continue to use this notation. I mean, more recently people have changed the notation, but we will not worry about that. We will still continue to use sigma g 2p. Right. What I am saying is that there is appreciable contribution from 2s also. Therefore, you cannot really say that this is sigma g 2p and that is sigma u star 2s and this is sigma g 2s, because there is appreciable contribution from the 2p orbitals also for these orbitals. Now, for analyzing these diatomic molecules, let me start with this picture, right, because this is a situation where 2p and 2s are not that much separated, and that will happen in the case of lithium, then in the case of Be2, C2 and so on. So, let me write this orbital order. That orbital order is actually sigma g 2p, sorry, sigma g 2s less than sigma u star 2s, which is less than pi u 2p, which is less than sigma g 2p, which is less than pi g star 2p, which is less than sigma u star 2p. Now, going back to Li2, lithium has the electronic configuration 1s2 2s1. So, it has only one valence electron. Thank you. So, it has only one valence electron, and remember we are not going to be interested in 1s2 electrons. So, we will consider only the valence electrons. These valence orbitals are the ones which form these molecular orbitals. So, therefore, in Li2 what will happen is that there are 2 electrons among these molecular orbitals. So, therefore, you will say okay, the electronic configuration of Li2 molecule is nothing but sigma g 2s with 2 electrons. Right. There is I mean, if you would like to have, I can also write 1s2 1s2. These are actually the lithium 2 lithium atoms. Right. The 2 lithium nuclei have 1s orbitals and their 2 electrons each are sitting. So, 4 electrons are accounted for here, and the remaining 2 electrons go to sigma g 2s. So, there are 2 electrons sitting in a bonding molecular orbital. Naturally, the bond order will be unity. Okay. The bond order in this case is unity. Let me denote it as bond order. It is equal to 1. And the bond length you find is 2.67 angstroms, which is actually surprisingly large. If you compare this with the case of hydrogen molecule, the bond length in the case of hydrogen molecule is 0.74 angstroms. So, one may ask, why is it that this bond length is very large? The reason is actually quite simple. You have these 1s electrons, they form the core, right, and these 1s electrons actually repel each other. So, the repulsion between the 2 1s core orbitals, I mean the electrons occupying the core orbitals, is the one that causes the bond length to be large, and in addition to that the 2s orbital is rather diffuse, meaning that it extends into space, and therefore, the overlap between the 2s is not very effective. That is the reason why the bond length is very large, and because the bond length is very large, the bond energy is actually low. It is only 105 kilojoules per mole. Just to compare, maybe I should write H2 here. H2 has 2 electrons in sigma G1s, right. H2 has 2 electrons in sigma G1s. Bond order actually is 1. Bond length is 0.74 angstroms. And the bond energy is how much? It is 431 kilojoules. Just to compare the two. Now, thinking of B2. B2 means that you have just added 2 more electrons. Okay, let me remove this part. I don't need this anymore. And if you have, maybe I will write this here, Li2, then Be2. You have added 2 more electrons, so you would have sigma G. You will of course have 1s2, which I will not worry about. I will not write them down. Sigma G 2s with 2 electrons and sigma U star 2s with 2 electrons. So, 2 electrons in a bonding orbital, 2 electrons in an anti-bonding orbital. So, bond order if you calculate, you will find it is 0, that is the bond order, and this predicts that B2 will not be stable, and this is in agreement with the experiment, right. This is what is nice about molecular orbital theory. Most of its predictions are in full agreement with experiments. Then if you think of B2, well, you will have sigma G 2s with 2 electrons, sigma U star 2s with 2 electrons, and you have to add 2 more electrons to the pi U 2p. Right. Pi U 2p is actually pi U 2p is actually doubly degenerate, right, because you have pi U 2px and pi U 2py, and so if you have doubly degenerate orbitals and if you put 2 electrons into them, what will happen? They will go and occupy the 2 separate orbitals. They will not get paired up because pairing means electron repulsion is larger. So, they will not they will not get paired up. If you want to represent it in this picture, then maybe I should do that. I have 2 electrons here, I have 2 electrons there, I have 1 electron here and 1 electron there. So, therefore, you have 2 unpaired electrons, and so you predict that the molecule will not be diamagnetic, but instead it will be paramagnetic, and this is in agreement with experiments. And then what about the bond order? Well, the bonding due to this is cancelled by the bonding due to that, but these are bonding orbitals and there are 2 electrons sitting in this bonding orbitals. So, therefore, bond order is going to be how much? It is going to be 1. And bond energy you can measure, it is found to be 289 kilojoules per mole. Okay. Then you think of C2. C2, what will happen? You will just add 2 more electrons. So, you would have sigma G 2s with 2 electrons, sigma U star 2s with 2 electrons, pi U 2p with 4 electrons. So, there are no unpaired electrons now in the case of C2. Calculate the bond order, you will find that bond order is actually equal to 2. This means that in the case of molecule C2, there is a double bond between the 2 carbon atoms. And naturally, the bond length will be short. It is found to be 1.31 angstroms, that is the bond length, and the bond energy is 627.6 0.6 kilojoules per mole, rather high. That is because there is a double bond. Then coming to N2, you just add 2 more electrons. So, therefore, you would have sigma g 2s, sigma u star 2s, pi u 2p 4, and then the next one, which is the orbital, it is sigma g 2p with 2 electrons. So, remember, you see this and that, they cancel each other because this is bonding, that is anti-bonding, but these are all bonding orbitals, and therefore, you have 6 electrons sitting in them. That means a bond order actually is 3, which means that there is a triple bond in the case of N2 molecule. Nitrogen molecule has a triple bond, and the bond length is short, it is 1.01 angstroms, and the bond energy is 941.4 kilojoules. And notice that the highest occupied molecular orbital is sigma g 2p. Now, this can be experimentally verified. You see, there is this technique called photoelectron spectroscopy, where you can remove an electron from the molecule by allowing it to interact with electromagnetic radiation, right. For example, UV radiation can cause emission of electrons from this orbital, from which you can actually find out whether it is a sigma type or a pi type orbital. Okay. So, the experiments indicate, photoelectron spectroscopic experiments indicate that this is a sigma orbital, the highest occupied orbital is a sigma orbital. Then you come to O2. As you go down, the separation in energy between the 2s and 2p atomic orbitals increase. As a result of which, what will happen? The orbital order gets interchanged. In the case of oxygen, what happens is that the orbital order is actually this one, right. This is the orbital order, and therefore, what will happen? It is the case that sigma g 2p has a lower energy in comparison with pi u 2p. So, therefore, the electronic configuration of oxygen will be sigma g 2s with 2 electrons, sigma u star 2s with 2 electrons. The orbital order is this. So, therefore, the next orbital is sigma g 2p with 2 electrons, and pi u 2p with how many electrons? With 4 electrons, and pi g star 2p will contain how many electrons? It will contain 2 electrons. Have I got something interchanged? It is actually this orbital order that you have to follow now, essentially because the energy separation between 2s and 2p is large, right. And therefore, you have this order, and if that is the way it is, you would find that there are 2 unpaired electrons in the case of oxygen molecule, which again is in agreement with experiment. Oxygen molecule has a bond order of 2, and bond length actually is 1.21 angstroms. It is predicted to be a double bond, because if you calculate the bond order, you get 2, and the bond energy is actually 493.7 kilojoules per mole. So, oxygen is predicted to be paramagnetic, because there are 2 electrons sitting in pi g 2p. Pi g 2p is doubly degenerate, so therefore, the 2 electrons are unpaired. Now, suppose I remove an electron from oxygen to get O2 plus. Okay. I do not have any space, let me just write here. If I suppose I make O2 plus, then what are you actually doing? You are removing one electron from this orbital, and this orbital is actually anti-bonding. This orbital pi g star 2p is anti-bonding. So, if you remove one electron, what you are doing is you are increasing the bond order, because you see one electron has been removed from an anti-bonding orbital. So, the system actually becomes more bonding. If you calculated the bond order, you will find that it is 2.5, right. So, instead of 2 for oxygen, it will become 2.5, and as a result of that, if you are able to measure the bond length, you will find that the bond length is 1.227 angstroms. Oxygen molecule itself has a higher bond length, it is 1.21 in the case of oxygen molecule, while O2 plus the bond length is shorter, because the bond length has increased, because the bond order has increased. On the other hand, if you made O2 minus, that means you are adding one more electron, what will happen? The bond order will actually decrease, it will become 1.5, because you are putting one electron into an anti-bonding orbital, as a result of which the bond length will actually increase, it will decrease to 1.26 angstroms. Finally, if you think of F2, well, you will have just one more electron. So, all these things can remain as they are, but the last orbital pi g star 2p now has 4 electrons. That means there are no unpaired electrons. See, everything else remains the same. You put 2 more electrons, so this will become pi g star 2p. If you calculated the bond order, you will find that it is equal to unity, and the bond length is 1.42 angstroms, and the bond energy is 151 kilojoules per mole. So, this way, I mean, all the homonuclear diatomic molecules can be their existence, their magnetic nature, their bond energy, bond length, everything can be very satisfactorily explained using the molecular orbital theory. And regarding heteronuclear diatomics, I shall very briefly indicate you how the molecular orbital theory is applied. The discussion will be very brief. In fact, these days it is possible for you to calculate, it is possible for you to make molecular orbital calculations for not only diatomic molecules, but triatomic or any big system. I mean, bigger systems, it's not very difficult these days, because the computer power available is tremendous these days. As a result of which, even if you had a big system, maybe you will have 60 carbon atoms or even larger number of carbon atoms and equally large number of hydrogen or oxygen atoms, it is not very difficult to do calculations using molecular orbital theory. Let us now think of simple heteronuclear diatomic, and this is the only example that I shall discuss. The molecule that I have chosen is LiH. In the case of LiH, what happens? You have the 1s orbital on lithium. Okay. This is the 1s orbital on lithium, and then you have the 2s and the 2p. These are on the lithium. Okay. And now you think of the 1s orbital on the hydrogen. Relatively speaking, you see its energy will be higher than that of 1s on the lithium, because you see lithium nucleus is having 3 positive charges, and a 1s orbital which is centered around that nucleus will have very low energy. So, relative to that, you see the 1s orbital on hydrogen will have a much higher energy in comparison with this. right. And in fact, the energy of this 1s will be lower than the 2s on the lithium, right. So, what will happen? This is very much low in energy. In fact, in this picture maybe I should move it even further down. As a result of which, what will happen? This orbital is not involved in the bond formation. This has little overlap with the 1s at the bonding geometry, and therefore, it is not going to interact. So, effectively what will happen? It is the 1s interacting with 2s. It will also have some interaction with appropriately oriented 2p orbital, which is actually 2pz. Okay. And what will happen? The 2px and 2py will not interact with the 1s. So, therefore, they will remain non-interacting in the molecule. So, therefore, if this is your molecule, the 2p orbitals 2px and 2py, they will not interact, and they have to be classified as pi type orbitals in the molecule, because if you rotate it about the z axis, you see if you rotate by 180 degrees, the orbitals change sign, okay, and there are 2 of them. So, this is not involved in the bond formation. Now, 2s and 1s will interact, but this 1s can also interact with 2pz there. So, therefore, what will happen is that the 1s, 2s and the 2pz all will mix together. 3 orbitals will combine together. If 3 atomic orbitals combine together, what do you expect to get? You would expect to get 3 molecular orbitals. So, therefore, you will have an orbital which is a bonding orbital, which may be something like this, and notice that it is in fact close to 1s, right. The energy wise it is close to 1s. Why? Because the 2s is having a higher energy. And then you will have an orbital which will be again a sigma type orbital, which will be having an energy like that. As I told you, 1s from the hydrogen and 2s and 2pz from the lithium are combining. So, 3 atomic orbitals are combining. When 3 atomic orbitals combine, you will get 3 new orbitals which are molecular orbitals. So, you will have an orbital of roughly that energy, and you will have one more orbital of energy roughly that much. And we need notation. What do we do? These are all sigma type orbitals. So, therefore, you will say this is a sigma type orbital, this is another sigma type, and this is the third sigma type. Okay. And to distinguish between them, what do? You put a 1 here. So, you call it 1 sigma, this you will call 2 sigma. It just simply means that it is the next sigma type orbital, that is all, and this you will call 3 sigma. And this one, to be correct, I will call it 1 pi, because it is the first pi type molecular orbital in the molecule. Okay. And how many valence electrons does lithium hydride? I mean, there are in the molecule. Lithium has 1 valence electron, hydrogen has 1 valence electron. So, there are only 2 electrons. So, naturally, those 2 electrons, they will sit in this bonding molecular orbital, and that is why the bond is formed. But then if you think of that orbital, you see it is rather close to the 1s, which means that this 1s actually makes a fairly large contribution to that bonding orbital, right. So, therefore, if I try to represent it pictorially, what will happen? I would have lithium and the hydrogen, but this is essentially having little contribution from the 2s, and a majority of the contribution will come from the 2s, sorry, not the 2s, but the 1s. 2s will have a small contribution, 2s and 2p together will make a small contributions, and 1s will make the largest contribution. So, therefore, if you put 2 electrons into this orbital, these 2 electrons will be mostly spending their time near the hydrogen, right. And therefore, in the case of LiH, you will find that there is a sizable negative charge on the hydrogen, and with an equally sizable positive charge on the lithium, right. In fact, the bond length, sorry, not the bond length is actually 1.60 in the case of lithium hydride, 1.60 angstroms, you can actually measure the dipole moment, and you find that the dipole moment of the molecule is 5.9 dBi, which is fairly large dipole moment, and that is because what has happened is that when the molecule is formed, there is charge transfer from lithium to the hydrogen, and that is why hydrogen has negative charge and lithium has positive charge. So, the bond is actually almost ionic, because you see ionic bond, what do you mean by ionic bond? Ionic bond is a situation where charge is transferred from one of the bonding species to the other, and there is almost 80% ionic nature as far as this bond is concerned. Sizable and charge transfer is there from lithium to the hydrogen, and that is why you say it is ionic. Okay, this is all that I will discuss as far as heteronuclear diatomics are concerned, but you can think of other heteronuclear diatomics. They are not difficult to consider, but we will not do it. And the next topic that I shall discuss is actually the ideas of hybridization. In fact, hybridization also would be taught in inorganic chemistry, but what I will do is I will give you a brief description constructing what are known as the hybrid orbitals, so that you will have a clear idea of the mathematics that is involved in the construction of hybrid orbitals. So, hybridization I shall illustrate this concept in using the molecule BeH2. Okay. Now, what is the electron configuration of Be? It is actually 1s2, 2s2, right, and well, if you think of beryllium atom, what happens is that you have 2s2, it is a closed shell system, and therefore, there are no unpaired electrons, and therefore, a chemist would have difficulty in understanding how bonds are formed, because you see the atom has no unpaired electrons. So, usually chemists will say that okay, if there are unpaired electrons, you will have the possibility of forming an electron pair bond. But the answer to that is not difficult, because the 2p orbitals are there, the 2p orbitals are close in energy to 2s. So, therefore, imagine that one electron is promoted from 2s to 2p, let me say 2pz. So, that you have one electron here, you have one electron there, now you have two unpaired electrons, and therefore, you can form two bonds, one with this hydrogen and the other with that hydrogen. Okay. But if that is the way it is, see, if you have 2s, one electron in 2s, which is going to pair with the electron of hydrogen sitting in 1s, and this is going to pair with the electron of the other hydrogen, right. So, that you have two electron pair bonds. This is essentially a valence bond way of thinking. So, if that happens, okay, then what would you expect? You see, one bond is formed because of pairing with 2s, the other bond is formed because of pairing with 2p z, and you would expect that the two bonds are not equivalent, because one is formed using 2s, the other is formed using 2p z. But then when you do an experiment measuring the bond length, so for the bonds in BeH2, you find that the two bonds are having the same bond length, and any experiment that you perform indicates to you that the two bonds are completely equivalent. And then to explain this equivalence, the concept of hybridization was introduced by Pauling. So, what he said was this: imagine that this 2s and the 2pz orbitals, these two orbitals, imagine they are mixed together. So, how are they going to get mixed together? Well, what would happen is that you have 2s and the 2pz. Imagine you have some coefficient A1 with which you multiply 2s and some other coefficient B1 with which you multiply 2pz and add the two together. This is how I will mix the two orbitals, and the result I will say is an orbital which is a hybridized orbital, which I will denote by the symbol phi 1. And in a similar fashion I can say, okay, I will take 2s, multiply it by A2, add to it 2pz multiplied by B2, and I shall get another hybrid orbital. So, therefore, we say we are adding linearly 2s and 2pz. Now, I shall also put the condition that these orbitals should have the same kind of nature, right. They have to be completely equivalent to one another. Maybe they can be oriented differently in space, but except for that they should be completely equivalent, correct. I will have to put that condition, and in addition any orbital that I use I would like it to be normalized. I would also like these two orbitals to be orthogonal to one another, because that is a property of orbitals. So, therefore, if I impose the condition that the orbital is normalized, what would that mean? Integral of phi 1 square d2 over the entire space must be equal to unity. That actually means, I mean, strictly speaking, again I should say phi 1 star phi 1, but these orbitals are all real. So, it is not necessary to put the star. So, if you applied this condition to that orbital, what it says is you take A1 2s plus B1 2pz, take the square, integrate over the entire space, the answer must be equal to 1, right. That is what it means. So, suppose you took the square, what is the result? You are going to get A1 square 2s square plus B1 square 2pz square plus 2A1 B1 2s into 2pz, and you are going to multiply by d2 and integrate over the entire space. Each term you are going to, this is B1 square of course, d2 you have to put integrate over the entire space, here again you have to put d2 integrate over the entire space. So, this integral is equal to that, and that should be equal to unity, correct. Now, remember your atomic orbitals are already normalized. A1 is just a constant which I want to determine, and this A1 can be taken out of the integral sign. So, you have 2s square integrated over the entire space. If your orbital is normalized, that has to be equal to unity. So, therefore, this will become A1 square, and in a similar fashion 2pz also is normalized. So, therefore, you will get plus B1 square, and further remember that 2s and 2pz are atomic orbitals on the same atom. They are not on different atoms, because I am thinking of atomic orbitals on beryllium. They are on the same atom. So, atomic orbitals belonging to the same atom are actually orthogonal to one another, and therefore, this integral is going to be equal to 0, and therefore, what is the result that I get? A1 square plus B1 square must be equal to 1, fine. And if you impose the condition that phi 2 is normalized, what is it that you get? You get the result that A2 square plus B2 square must be equal to 1, fine. Then suppose I multiplied the two orbitals, I multiply phi 1 into phi 2 and integrate over the entire space. What would be the answer? The answer is actually, right. I mean, if you multiplied these two, you are going to get terms like A1 A2 2s the whole square, right, d2, that will be one term if you multiplied the 2, and you will get B1 B2 2s 2pz, sorry, not 2s 2pz, but 2pz square d2. This is another term that you will get, right, and you will also get terms which involving 2s into 2pz integrated over the entire space, but that integral 2s into 2pz integrated over the entire space is actually 0. So, it is not necessary for me to consider the cross terms. So, effectively what will happen is that you are going to get 0 here on the right hand side, because the two orbitals I want them to be orthogonal, but this integral is how much? This integral is unity, that integral also is unity. So, effectively the condition becomes a1 b1 sorry a1 b1 plus a2 b2 must be equal to 0. Okay. So, therefore, our orbitals hybrid orbitals phi 1 and phi 2 I want to determine them, and I want them to satisfy these conditions. Okay. Now, if you look at this expression, see phi 1 is given by a1 plus a1 into 2s plus b1 into 2pz. Okay. And further I have also found that a1 square is actually the coefficient of 2s square, and b1 square is actually the coefficient of 2pz square, if you think of phi square. And this means that the importance of the 2s orbital in the orbital phi 1 is actually determined by a1 square, or in the charge density of phi 1 square, the importance of 2s orbital is determined by a1 square, right. So, therefore, you can say okay, a1 square is the contribution of the 2s, b1 square is the contribution of the 2pz to the orbital phi 1, and similarly a2 square is the contribution of the 2s, and b2 square is the contribution of 2p to the orbital phi 2, right. So, if that is the way it is, I can say that okay, I want the two orbitals to be equivalent, fine, I want the two orbitals, two hybrid orbitals to be equivalent, and that means that magnitude wise a1 square must be equal to a2 square, and also that means that b1 square must be equal to b2 square, right. I want a1 b1 square to be equal to b2, because you see the orbitals should have the same p contribution, they should also have the same s contribution, and to ensure that you can say these two have to be equal, you should have these two also equal, right. So, using all these equations, you see it is a fairly straightforward matter to solve for a1 and b1 and a2 and b2. If you solved them, what is the answer that you get? You find that a1 must be equal to 1 by square root of 2, you can choose b1 to be equal to 1 by square root of 2, a2 to be 1 by root 2, and b2 to be minus 1 by root 2. The easiest thing to do will be I claim that these are the solutions, and what you can do is you can substitute these things in here and see that these equations are satisfied if I chose a1, b1, a2, b2 to be having these values, right. And therefore, I have found two hybrid orbitals. What are the hybrid orbitals? The first hybrid orbital is phi 1. Phi 1 actually has 1 by root 2 here, 1 by root 2 there. So, you get 1 by root 2 times 2s plus 2pz, and phi 2 would be 1 by root 2 times 2s minus 2pz, fine. And so, if that is these are the hybrid orbitals, let me try to draw them. See, this is my 2s, which I represent by a sphere, and that is my 2p z. The 2s is positive, you can say the 2s orbital is having a positive value, let us say. And so, if you added the 2 up, suppose you add the 2s with the 2pz, what will happen? Well, in these regions both 2s and 2pz are positive. So, therefore, you will have a positive region which may be represented by a lobe of this shape, and in this region what will happen is that the 2s has a positive sign while 2pz has a negative sign. So, therefore, they will tend to cancel each other, but the 2s is actually extending in this direction. So, therefore, you will be left with a negative lobe, something like that, but it will be much smaller, and somewhere here you will say is your beryllium nucleus. Okay. Then if you constructed the other hybrid orbital, which is phi 2, how will you construct that? Well, you have to multiply 2pz with minus 1 and then add. So, if you multiply 2pz with minus 1, this will become negative and that will become positive, and then if you added them up, what is the result? The result is you will have the beryllium nucleus here, and you will have a positive lobe which is pointing in this direction and a smaller negative lobe on the other side. So, if you have the beryllium atom, what happens is that one hybrid points in that direction and the other hybrid points in the reverse direction, right. So, that the angle between the two hybrids is actually exactly 180 degrees, because they are pointing in different directions along the same line, which is the z direction. So, then what will happen? This may be used to form a bond with the hydrogen on this side, and this will be used to form a bond with the other hydrogen on the other side, and therefore, if you had beryllium hydride BeH2, these two bonds are formed by hybrid orbitals which point exactly in the opposite direction, as a result of which the bond angle works out to be 180 degrees, and you can see that the two hybrid orbitals are completely equivalent to one another. Okay, here I have a Mathematica file which shows the shape of these orbitals. Unfortunately, it has become too big. Okay, now it has become too small. Okay, this is the one of the hybrid orbitals which is pointing towards one of the hydrogens. You can see it from different angles. Somewhere here is the beryllium atom, and you can actually rotate it and view it from different angles if you like. Similarly, this is the other hybrid orbital which is pointing in exactly the opposite direction. This is only one way of representing the orbitals. I can think of other ways of representing the orbital, and this, for example, is another way of representing the orbital. Okay. So, this is a hybrid orbital which is represented using contour diagrams, and you will see that this orbital, this hybrid orbital is pointing in this direction. And you have another hybrid which is shown down here, I believe, yeah, there it is, and it is pointing in exactly the opposite direction. Okay. So, these are the two orbitals. One is this one and this is the other one. Unfortunately, I should also point out that this is the labeling here is not correct. This is called is x, but it should have been called z, because the orbitals are pointing in the z direction. And this type of hybridization actually is referred to as SP hybridization, because in this case one s orbital, that is the 2s, and one p orbital, that is actually the 2pz, these two combine and give you two equivalent hybrid orbitals. Okay. So, therefore, this is referred to as SP hybridization. But you would already know that there are other systems. For example, if you have the molecule BCl3, a molecule involving boron, if you have BCl3, what would have is you have boron with the electronic configuration 1s2, 2s2, 2p1, but it is able to form 3 bonds, 3 equivalent bonds. And therefore, just as in this case, what you will say is, okay, one electron is promoted from here, and so you have 2 unpaired electrons sitting in 2p orbitals and 1 unpaired electron sitting in the 2s. And then these 3 orbitals, so 1 2s and the 2 2p orbitals may be mixed together to give you hybrid orbitals. Okay. So, let us try to do that. I will say that I have my boron here in this at the center of my coordinate system. This is my x axis and that I will say is my y axis. Okay. So, I would have the 2s orbital, I would also have 2px and I would have 2py. So, what is the problem now? The problem is that I would like to mix these 3 orbitals, 2s, 2px and 2py, and to get hybrid orbitals, 3 of them, which I will denote as phi 1, phi 2, phi 3, and they should all be completely equivalent to one another. Thank you for listening.